Okay, so in the previous class, we have seen like what is the advantage and like what is the need of an epitaxial layer growth and how the epitaxial growth is divided into two different types, and that is homoepitaxy and heteroepitaxy. So homoepitaxy means uh, silicon substrate is there, and if we are depositing a silicon layer onto the silicon substrate itself, that will be considered as homoepitaxy. That means the substrate and the film that we are growing, that should be having the same material type. So in homoepitaxy it could be type if we are uh, having a silicon substrate, so substrate could be either p type or n type. Okay, so suppose p type is there and we are depositing n type, n plus n type layer. Okay, so these layers will be like of silicon itself, and this p type is also having silicon, so this are of same material is used in both the layer depositions. That is called homoepitaxy. In heteroepitaxy, suppose we are having silicon, okay, but we are growing a layer of aluminum arsenide that is different from silicon material. Okay, so if we are growing a layer of aluminum arsenide, so it is different from the silicon, so it is called hetero. Okay, and this is called homo. So these two we have seen. Next we will see like what are the different types of epitaxial growth, and these are like steps that should be followed while growing epitaxial uh, process in epitaxial layer. So in that, absorption of dopant atoms, surface diffusion, crystal growth, and then evaporation of dopant atoms. So these are the different steps that we will be following while depositing an epitaxial layer, that we will see in detail into the next discussions. And the parameters that we should be keeping in mind to have a better epitaxial layer growth is the temperature that we are using, the pressure effect, what is the pressure and temperature effect onto the epitaxial layer growth, and the flow amount of reactant. So in epitaxial layer, based on the different type of techniques that we will be using to deposit an epitaxial layer, we used to flow the dopant in the form of gaseous or chemical. There are different types. Okay, so what amount of reactants or dopant we are flowing, that is also one of the parameters for better epitaxial growth. And also the substrate and the treatment. So what type of substrate is there, with respect to that, what type of flow, gas flow should be there. These are the parameters we should be keeping in mind while having an epitaxial layer growth. This is the basic schematic, or you can say basic method that is used for epitaxial deposition. So epitaxial layer growth means we are, okay, so this is a substrate will be there, and in that what we will be doing is we will be we will be placing the substrate onto a reactor. Okay, so suppose a reactor there, we will be placing a substrate. Onto the substrate we will be flowing a gas, or we will be having a bulk flow that will be in the form of chemical or in the form of gas. Okay, and this will be flowing. Okay, different reactant will be allowed to flow, and this is outlet, you can say. Okay, so the same gas or whatever bulk we are giving as an input, the same will be taken it out. And while flowing this, there will be some of this reactant that will be reacting to the substrate, whatever substrate we are using. So this uh, bulk atoms or bulk that we are using, that is in the form of chemical or in the form of gas, so this gas atoms will be having some chemical reaction to the substrate surface. Okay, So this is substrate surface. There will be some reactions that can be a chemical reaction. Okay, so these are different bulk atoms are there. These are being deposited onto the substrate. So this is deposition. So this the deposition is considered as growth. Okay, so these are deposition of the reactant that we are flowing. So these are reactants basically that are having doping atom. Okay, so that will be flowing through the substrate and there will be a deposition, some chemical reaction. Okay, so this is the basic idea, like how we should be depositing a layer onto the substrate. Okay, so next we will see like what different types of techniques that are used to grow or deposit uh, layer of epitaxial material onto a substrate. So this is the basic idea. A substrate will be there and we will be flowing a gas or chemical such that that gas or chemical will be having some reaction to the substrate surface, and after reaction some event atoms will be deposited onto the substrate, and this layer, whatever layer is being deposited, this will be called epitaxial layer. Okay. This is the basic idea. Okay. So the basic epitaxial layer is basically grown, epitaxial layer is grown by using different temperature and pressure conditions. Onto that, it will be such that the method, like if we are having the bulk we are using, if it is a chemical, if we are providing a chemical, if we are providing a gas. Okay, so in terms of gas, if gas is being flowed, this will be called a vapor phase epitaxy. So if the reactant, the bulk, or we call it a reactant that we are providing, that reactant is in the form of gas. So that type of epitaxial process is called vapor phase epitaxy. Okay. Or in chemical that is in the form of liquid. Okay, so any reactant is there that is in the form of gas, that will be a vapor phase epitaxy. Okay, if it is in the form of liquid, okay, so the same bulk is in the form of liquid, this will be called liquid phase epitaxy. Okay, so here we will be basically focusing on vapor phase epitaxy, and along with that there is another method that is called molecular beam epitaxy. Okay, another method is called molecular beam epitaxy. So in molecular beam epitaxy there will be no chemical reaction taking place, no chemical reaction is there into the beam epitaxy, molecular beam epitaxy. In these two methods, LPE and VPE, there will be some chemical reactions, some chemical reactions taking place between the substrate and the reactant, and after some chemical reaction there will be a deposition, or we call it precipitation of the doping atom onto the substrate of the sample that we are going to have an epitaxial deposition. Okay. So we will see basically in our syllabus we will be basically dealing with the vapor phase and molecular beam epitaxy, these two, and before that we will be going through the liquid phase also, like what is the basic idea into this liquid phase epitaxy. Okay, so in liquid phase epitaxy, the reactants and the substrate both are you can say uh, used in the form of liquid, that is it is in the form of molten state. So suppose a reactant is there, like gallium arsenide is there, okay, and a substrate on which we are going to deposit is gallium. On gallium substrate we want to deposit gallium arsenide, okay. So what we will be doing is we will melt it, the gallium also we will melt it, and we will melt this gallium arsenide also. After melting we will be dissolving these two. Once these are melt in the form of melt, we will be dissolving, okay. So this melt is dissolved, okay. So this melt will be dissolved such that these are little like these are a soluble chemicals, like it will be dissolved to each other. Once it is dissolved, and that is always that is already in the form of molten. So once it is dissolved, it is in the form of molten, then it is cooled, okay. So once it is cooled, once it is cooled, it will be such that gallium is there and this is gallium arsenide. So it is like the gallium is cooled, and after cooling these two will be having different cooling temperatures, like, okay. So once one is cooled, then the second one will be cooled onto the surface, okay. So this will be like on gallium another layer of gallium arsenide has been deposited. So this is called this is called liquid phase epitaxy, okay. So in this type of epitaxial processes, what happened, there is this type of process, this liquid phase epitaxy, basically not used for silicon, okay. So this is not used for silicon. So why it is not used for silicon? Because it is very difficult to melt this silicon, okay. So that's why we will not be using liquid phase epitaxy, because in liquid phase epitaxy we need to have a molten form of the reactant and the substrate, okay? So in silicon based devices, this melting of silicon is very difficult, a complex process. So this liquid phase epitaxy is generally not used for uh, silicon type of devices, okay. The next one is molecular beam epitaxy. So in molecular beam epitaxy, as it is a method in which chemical reactions will be taking place, okay. So this is one of the complex process, okay, but it is one of the promising technique, one of the most reliable technique, you can say, in terms of liquid phase epitaxy and vapor phase epitaxy. Molecular beam epitaxy is the best among this, and also it does not have any chemical reactions. So there are a better deposition, the quality of epitaxial growth will be better in case of molecular beam epitaxy, okay. These molecular beam epitaxy we will see later in detail also. This is just an overview. In case of vapor phase epitaxy, so here the reactant will be in the form of gas, okay. So this gaseous form of reactant will be flown through the surface of your uh, substrate, and there will be some chemical reactions taking place between the atoms available into the gaseous form with the chemical with the surface of the reactant and the surface of the substrate. So based on the reactions, there will be a deposition of layer onto the surface of the substrate, and this method is your vapor phase epitaxy. So we will see this vapor phase epitaxy in detail, and what type of different reactors are used to have this type of deposition. We will see that also. Okay. And there are different other methods are also there. So like MOMBE, okay, sputtering, hydride, vapor phase epitaxy. There are different lot of methods. Okay, you can just go through it by self and have uh, the basic understanding, like what are the different types basically. Okay, so in case of vapor phase epitaxy, okay, so in case of vapor phase epitaxy, basically different components are used, like the reactant, that is in the form of gas, that will be in gaseous form, and there is a reactor that we should be requiring, and substrate, or we call it as sample on which the vapor phase epitaxial should be grown. Okay, so the basic idea of vapor phase is like there will be a support. Okay, onto this support different samples of substrate will be placed. So the fabrication process is basically done in the form of, I can say, bulk form. It should be done in the form of bulk, so that the cost of the fabrication can be reduced. Okay. So we cannot go for a single transistor fabrication, that will be very costly. So at a single time there are lots of transistors and ICs are fabricated at the same time, so that the effective cost can be reduced. So here similarly, this is like uh, sample holder, you can say. Okay, we can call it a sample holder. A sample holder will be there. Onto this sample is used. So this is our sample, or we call it substrate, on which the deposition of the epitaxial layer we want. So in that, this is placed like that into a chamber. Into that we will be flowing a gas. Okay, there will be a controlled flow of gas. So this there is basically a controller. This is called mass flow controller. So what should be the speed and what type of gas we should be flowing, that is controlled by mass flow controller. Okay, so here once we are flowing the gas, it is like going like that. Okay, so this is how the gases flow is controlled by mass flow controller, and it is placed into a chamber. Okay, and this is the sample holder. Samples are placed here. So once the gas is passed through the sample, there will be the deposition, or we call it, there will be some reaction between the gaseous molecules and the substrate. Okay, so based on the reaction, there will be a deposition of a layer onto this substrate. Okay, so this layer deposition will be considered as an epitaxial layer growth. So this flow, so how the quality of deposition depends is decided by different parameters basically. Okay, so as this is a gaseous flow, so if it is a gaseous flow, so the flow of a fluid or a gas is basically represented, basically the characteristics of gaseous flow is basically characterized by Reynolds number given by Re, that is Reynolds number. This Reynolds number is given by the formula that is called dr. This dr is diameter of the reactor tube. So whatever reactor tube we are using, through which we are flowing this gas, so the diameter of reactor tube is dr. Then the velocity of the gas, we are flowing, and rho divided by mu. So this rho is called gas density, and mu is called gas viscosity. And this V is gas velocity, and this is diameter of the tube, reactor tube, or tube we can call a reactor tube. Okay, so this is how the Reynolds number is given. Okay, so in this process of vapor phase epitaxy, the flow of gas basically should be a controlled flow. Okay, so the flow of gas is of basically two types. One is laminar flow, another one is called turbulent flow. So in case of vapor phase epitaxy, the flow of this gas should be of the form laminar flow. So in this laminar flow, the value of Reynolds number should be less than 2000. So this Reynolds number is a dimensionless quantity. It is a dimensionless. Okay, so this Reynolds number, if Reynolds number is less than 2000, that is called laminar flow, and this Reynolds number is greater than 2000, this is called a turbulent flow. But in case of vapor phase epitaxy, this Reynolds number is basically very less uh, in practical. Okay, but it should be less than 2000. Okay, so this flow should be an laminar flow. Okay, so basically here dr is the diameter of the tube on which this sample is placed, and the velocity, and this rho and mu, is the parameter that is decided by the gas that we are using. So this cannot be, you can say, this cannot be controlled by the user basically. Okay, it is material constant. So the only parameter that is here is the diameter of the tube or the velocity. So this Reynolds number can be controlled by basically the velocity and the diameter of the tube. So here the velocity is one of the parameter. Velocity is one of the parameters. So we will be seeing like how this velocity is going to affect the Reynolds number, and we should be selecting this velocity such that the Reynolds number is always less than 2000. And also the deposition that is basically done onto the surface. So this, what type of boundary layer is there? Okay, so this is the what is the deposition of this uh, epitaxial layer onto the surface is basically given by a parameter called y. Okay, so another parameter is there that is called y. So this y is basically given by drx dr into x divided by Reynolds number with the power 1 by 2. Okay, so here this x is the distance basically. So as we will be flowing from this point to this point, this is like x is increasing. So at the starting of this sample holder, the velocity of gas will be small than the velocity of gas at this location. Okay, so that means as the x is increasing, the velocity of gas increases. Okay, so based on the velocity of gas, the quality of deposition of epitaxial layer near this x, you can say if x is less or x is lower, then the deposition will be different from the deposition at this point. Okay, where x is high. So this is one of the parameter we should be considering while having the deposition in terms of epitaxial layer growth. Okay, so this x is given by the distance along the reaction chamber. So whatever reaction chamber is there, along this reaction chamber there will be uh, length that is going from this length to the other length. Okay, so it is from higher, here it will be 0 to the maximum, x will be maximum here. So once we are going from lower length to higher length, there will be some change or some quality change will be there onto the deposition of the surface. Okay, one of the another parameter that is defined as J, that is called the flux. So flux is like what is the change in the gaseous concentration. So what is the change in the concentration between this the atoms present in the surface and the gaseous molecules? There will be a concentration change. So with respect to that, there will be a change in the deposition also. Okay, so here this parameter d, change in the concentration, that is given by dn divided by the dy, or change in the uh, thickness of the boundary layer. Okay, so this is like a boundary layer. Okay. So this j in another term it is given by d and g minus ns divided by basically the y. So this ng is ng and this ns, ng and ns, or the concentration of surface, concentration of surface, and the gas. Whatever gas molecules are there, what is the concentration of gas? This is surface, and what is the concentration of gas? So this difference is given by dN, this concentration gradient. Okay, so this concentration gradient with respect to two different layers. So this is the layer 1, 2, and different layer gases will be there. So if this difference is high, then flux will be high. Okay, so this is like in original, there will be some difference. If the flux is high, then the deposition of this epitaxial layer will be better. Okay, so this J we need to have a high value. So this J should be high, that means flux density should be high, so that the deposition of epitaxial layer is better, and it is given by this formula. So here in the denominator we have Y, so that means the thickness of this boundary layer. So this is the thickness of this boundary layer basically is given in terms of if this thickness is high. Okay, so if this thickness is high, then JD will be less. That means if the boundary, this is equal, call it the boundary layer basically. So this is the boundary layer that so if boundary layer is high, then the flux density, or you can say flux, is basically low. So if flux is low, the deposition of the epitaxial layer should be of poor quality. Okay, so to have better deposition of epitaxial layer, this boundary layer should be low. Boundary layer should be reduced, you can say. So to have relation, you can see like, so if this boundary layer is dependent on x value. Okay, so this x value is like, if we are increasing the x, the boundary layer should be high. Okay, so near to this x is equals to 0, the boundary is close to this substrate, but as we are moving towards higher x value, the boundary layer has increased. So this boundary layer is increased, that means if boundary layer is increased, that means the flux will be less. Okay, from there, if Y is high, this J value will be low, so there will be a poor deposition on this substrate. So here this substrate will be having better deposition of epitaxial layer, and this will be having poor epitaxial layer deposition. Okay, so we should be avoiding this so that we should be having a uniform deposition of epitaxial layer. Okay, so to have a better deposition, the flux should be high, and to make this flux high, Y should be reduced. To reduce Y, okay, we should be reducing this x value. Even if we are changing the value of this Reynolds number in terms of velocity. So the relation between y, the boundary layer, and the velocity, we can see from here. Like once we will be putting this, r is directly proportional to v, so v will be in denominator. So like y will be inversely proportional of under root v. So if we are increasing the velocity, the y should be high. Okay, but y should be low to have a better deposition. So to have y low, this should be high, but this velocity should not be that much of high, so that this Reynolds number exceeds 2000. Okay, so have this velocity increased, y will be reduced, that will be our requirement, but this y should be such that this v should be increased such that our Reynolds number is within the limit of. So this is how the internal physics or chemical reaction kinematics, whatever kinetics of vapor phase deposition, vapor phase epitaxy is going through. That is the internal process. This is just an overview, like uh, the basic understanding of vapor phase epitaxy and what is its internally kinetic reactions, or different reactions are taking place, and we will be seeing the next. Okay. The next will be like once this is introduction part of Weber phase epitaxy, like and one more thing, like here the mass flow, whatever gases we are flowing. So this is deposition. So based on the substrate deposition, suppose on silicon we are depositing another silicon. So what type of gas should be required? That is different for different type of substrate. If a substrate is of another type, the uh, mass flow controller will be allowing only that type of gases that is suitable for that particular substrate. Okay, so this is the general basic setup. Now we will see the next different type of reactors basically used for Weber phase epitaxy. So here there are three different type of reactors are used. Okay, so here one of the reactor is horizontal one, another one is vertical, another one is radiant barrel type of reactors. Okay, so basically the reactors are divided into two types, horizontal and vertical. Okay, so in horizontal, the gas flow of reactants are parallel to the susceptor surface. So whatever surface is there, to this surface the gas flow will be in parallel with this surface. So if this gas is flowing this way and this is also the surface, so like in the previous one we have seen, this is the substrate and we are flowing the gas, it is parallel to the surface, the surface. So this is called uh, horizontal flow. Okay, so it is a very simple design. So in the previous design, initially what it was like, uh, this was the surface on which we have put the sample and we are flowing the gas. So gas we are flowing was such that here it was receiving a better deposition, here it was uh, poor deposition of epitaxial layer. So to avoid this, the support, the holder we have placed there, it is used in the modified form, like it is used in tilted or inclined form. Once it will be inclined form, because here the boundary layer was higher, so to reduce this boundary layer, what is done is in the reactor the samples are placed onto an inclined surface, you can say. Okay, so this will be as inclined holder, onto that the substrate will be placed, the wafers will be placed on which the deposition, epitaxial layer deposition will be there. Okay, so this is called horizontal deposition. So it is simple to design and can have many samples at the same time. Okay, so this type of reactor have the advantage of, like, you can place large number of samples at the same time. Okay, that means it can be used for bulk production. Okay, the next type is vertical. So in vertical flow, the gas flow of reactants are normal to the susceptor surface of the or the sample surface. So whatever surface is there in which the samples have been put, and the flow of gas. Okay, so gas will be flowed vertically to the surface. Okay, it was flowing horizontally, here the vertically gas will be flown. Okay, and uh, this is into this reactor, there is also this uh, heaters are used. Okay, so to heat this environment, so this uh, could be a electric heater, or we can have an RF heater that we have seen in the growth method also. So the similar type of structure is there, there will be some heater. So here also the heater will be here and gas will be flowing vertically to the surface and it will be exhausting out. Okay, so this is your vertical type of reactors. So here the in this vertical type of reactors, it is just by observing you can see like it is a complex design, and also we cannot place large number of samples at the same time, because we are flowing this gas vertically. Okay, so if it is flowing vertically, we can have smaller samples only near to this opening through which we are providing the gas. Okay, we cannot have a large sample, so that once air is or gas is passing through this hole, the near to this opening, only the surfaces will be having the vertical gas flow. All other will not be having the vertical gas flow. So this idea of vertical reactors are nullified basically. So we cannot have large number of samples at the same time. Okay. And also in case of horizontal reactors, as we are using horizontal reactors, there will be a boundary layer problem. So boundary layer, that is in the previous we have seen this is boundary layer. Okay, so there will be a boundary layer problem in horizontal type of reactors, but in case of vertical reactors there will be no boundary layer of layer problem. Okay, and also this is complex and cannot place too many samples. And one another type of barrel type reactors are used. So this is like uh, a barrel holder will be there. Onto that there will be some grooves, holes are will be there. Into this holes we will be placing the samples. Okay, samples will be placed and the gas flow will be parallel to this. So this is sample, the gas is input here and they are flowing parallel to this surface, parallel to surface. So it seems like a vertical one, but it is a horizontal type of reaction, a reactor. Okay, so here the gas is flowing parallel to this surface. So this is called horizontal type of reactor. It is called radiant barrel type. Okay, so these are different reactors that is used for vapor phase epitaxy. Uh, Next we will see the molecular beam epitaxy. Okay,